All right, let's go ahead and get started. I do want to welcome you to this final installment of Unit 14, General Equilibrium. Now, in this particular installment, we're going to be looking at some advanced topics in equilibrium, and they include the relationship between equilibrium and thermodynamics to begin with, and then equilibrium and reaction kinetics. So if you're not thoroughly familiar with those topics, you're probably better off holding off on these advanced topics and then waiting until you're more familiar with thermodynamics and reaction kinetics. So here we go. Let's start with the relationship between equilibrium and thermodynamics. All right, so you should be familiar with these curves that I'm showing here on the left and the right. These are potential energy curves, and what they show is the relationship as the reaction progresses between the reactants and the products. Reactants, of course, on the left, products on the right. So on this curve that I'm showing here on the left-hand side, right, what we've got is this. What we've got is an exothermic reaction. It's an exothermic reaction because products are lower in potential energy than reactants, right? Products are lower in potential energy than reactants. So how do I relate that to an equilibrium constant? Well, I'm going to ask the question, is it easier for me to move in the forward direction or the reverse reaction? Reverse direction. So if I look on the forward reaction, I have a little hill to climb in the forward direction, and then I slide down the backside of that hill. But if I try to go the other way, then I've got a big hill to climb. So for an exothermic reaction, then the forward reaction generally is favored, right? The forward reaction is favored. And so that's not to say that we don't have a reverse reaction. We certainly do. But in any equilibrium, we're going to have a forward and a reverse reaction. But the forward reaction is going to be the one that is favored. Now, that having been said, we're going to ask the question, then how does that relate to the equilibrium constant? Well, remember that the equilibrium constant is products over reactants, right? Products over reactants. So if the forward reaction is favored, that means that generally speaking, K is going to be greater than 1, right? K is going to be bigger than 1 for an exothermic reaction. Now let's look at an endothermic reaction. For an endothermic reaction, we've got a delta H that is positive, right? Delta H is positive because the fact that as we move from left to right, the reverse reaction is favored, right? The products are higher in potential energy than our reactants. And therefore, because of that, the reactants are going to be in lower concentration than will be the products. And for endothermic reactions, in general, K will be less than 1. So let's just review. What's the relationship between potential energy in a thermodynamic situation and equilibrium constants? For an exothermic reaction, K is going to be bigger than 1 because products are favored over reactants. For an endothermic reaction, the opposite is true. Reactants are favored over products, and therefore K would be less than 1. All right? So that'll do it for the relationship between general equilibrium and thermodynamics. What we want to do now is we want to look at the relationship between equilibrium and kinetics, right? So let's take a look at this particular mechanism. It's a three-step mechanism where A and B form C. That's the equilibrium step that goes back and forth, and it's fast, by the way. The next step is the slow step, and the final step, the third step, is D converted to E. Again, that is a fast step. So at this point, if I were to ask you to write the rate law for this mechanism, you would use the rule that, well, I'll go to the slowest step and write the rate law from the slowest step. There's only one reactant in the slow step, and that is the C right here. So rate then would equal to some kinetic or some rate constant, I'll call it K, times the concentration of C. There's only one, there's no coefficient there, so I'll just say it to the first power. So this would have been the rate law from this mechanism, right? But we've got a problem. And the problem is that C, which is in the rate law, doesn't show up in the end, and it's not there at the beginning. It's what we call an intermediate, right? C is an intermediate. When it doesn't show up at the beginning or the end, it shows up in the middle and then disappears, we call that an intermediate. Well, you don't see the intermediate in the laboratory situation. So you have to have a rate law that's written in terms of something other than that intermediate. How do we do that? How do we go about that? Here's how we do it. What we do is we go to the equilibrium step. It's generally going to be the step just previous to the slow step, and it certainly is in this case. So this is the equilibrium step right there. And what we're going to do is we're going to write the equilibrium expression for that equilibrium step. In this case, it's Kc is equal to products of C over reactants, which are A and B. No coefficients involved, right? So now what we're going to do is we're going to isolate the intermediate. We want the intermediate by itself. So C then is equal to, that's the Kc, I'll pull A and B up. And so C therefore would be equal to, the concentration of C would be equal to this. Kc times the concentration of A times the concentration of B. Now watch what I'm going to do. I'm going to go back to the original rate law that I wrote, and I'm going to rewrite it, this time making a substitution. We know that concentration of C is equal to Kc times concentration of A times concentration of B. So I'll make that substitution. So we have rate is equal to K. That K is this K right here, right? It's a rate constant. I'm going to multiply that by an equilibrium constant that I'll call Kc, right? So that's multiplied right there. So K times Kc times concentration of A times the concentration of B. Now, we're almost done, right? The only thing that we need to recognize is that these two numbers, even though one is a constant for equilibrium and the other is a concentration for rate, they're both constants. They don't change. And therefore, we can consolidate them into a single constant. I'll call that K prime, right? I'll call that K prime. So in the final rate law, we'll write it as rate is equal to K prime times the concentration of A times the concentration of B, and that is the rate law that we'll use. Okay? All right. Let's go to a problem with some real chemicals in it. Let's take a look at this one right here. Okay? Here's what it says. The formation of nitrosyl bromide, NOBr, has the following proposed mechanism. All right, so here it is. It's a two-step mechanism this time. Fast step is the equilibrium step, followed by a slow step number 2. So we have in the fast step, NO plus Br2 in equilibrium with NOBr2. In the second step, we have NOBr2 plus NO yielding to NOBr. That's the slow step. So if I wanted to write the rate law for this mechanism to begin with, to start with, I would go to the slow step and I would write the mechanism based on that slow step, right? Based on that slow step. So I would say rate is equal to K, that's a rate constant, times NOBr2, that's one of the reactants, times NO, that's the second reactant, and that would be my rate law. But I have a problem. And the problem is that I recognize that NOBr2 is an intermediate, right? It cannot be in the rate law. It cannot be in the rate law. So how do I deal with that? Well, what I'm going to do is I'm going to go to the previous step, the equilibrium step, and I'm going to write the equilibrium constant for that step. Products over reactants. So we have NOBr2 over NO over Br2. That's the equilibrium constant. And I'm going to solve for NOBr2. That's the one I'm trying to get rid of. So to do that, I'm going to pull the NO and the Br2 up. And when I do that, I get Kc times, that's multiplication, Kc times NO times Br2, and that's equal to NOBr2. Okay, now what I'm going to do is this. I'm going to rewrite the rate law. I'll do it over here as rate is equal to K, this K is this K, times Kc, this Kc is this Kc, times NO times Br2, but don't forget the original NO, right? So times NO, right? Let me go through that again. I'm rewriting the rate law now. I'm saying rate is equal to K. This K is the rate law K from the original rate law, the one that I cannot use because it has an intermediate in it. times Kc. Okay, so I'm going to replace this NOBr2 with Kc times NO times Br2. So here's that part right here, right? But don't forget the other NO right there. So that NO has to be included as well. So I'm going to consolidate everything, and I'm going to write the rate law as rate is equal to K times Kc, remember, is just a constant. I'm going to call it K prime times NO or NO squared times Br2, and that, my friends, is the rate law. All right? All right, let's go ahead and get started with this last problem. It says the synthesis of HBr proceeds via the following steps in the gaseous state. So it is obviously a three-step process. In the first one, we have Br2 becoming in equilibrium with 2Br. That's a fast equilibrium step. The second step is the slow step. We have Br plus H2 in equilibrium with HBr plus H. And then we have hydrogen plus Br2 in, becoming in a fast step HBr and Br. All right? So how do we do this? Well, the first thing we're going to do is we're going to look to the slow step. We're going to write the rate law based on that slow step, and what we discover then is that there's an intermediate involved, and that intermediate, of course, is Br. So I write the slow step, though, as rate is equal to some rate constant times Br times H2, and recognize once again that Br is an intermediate. So I have to rewrite the rate law a rate law that does not include that intermediate. So the way that I'm going to do that is to go to the previous step, the equilibrium step. It's a fast step, and I'm going to write the equilibrium expression for that step. So here's what we've got. We've got Br2 or Br squared, 2Br would become Br squared over Br squared to the first power, right? So what I want to do is I want to solve for the thing that I'm trying to eliminate. In this case, it's the Br, right? I'm trying to get rid of that because it's on the left and the right-hand side of those two equations, 1 and 2. So here's what we've got. We've got Kc then is equal to Br2, right? Is equal to Br, or the concentration of Br squared. Now we're going to have to deal with that squared by taking the square root of what we have on the left-hand side. Remember, we're trying to isolate Br by itself. So we have Kc to the 1/2 power. I just made each of these to the 1/2 power times Br2 to the 1/2 power, and now I've got the Br isolated, right? So let me rewrite this rate law now as rate is equal to K. So this K is this K, right? Times, now let me make the substitution. Br is Kc to the 1/2. There should have been a C right there. Kc to the 1/2 times Br2 to the 1/2 power, right? And now don't forget this H2 right here. Don't forget that last hydrogen gas right there that also is part of the rate law. So rate then is equal to, now what I'm going to do is I'm going to recognize that these two right here, this K and this K to the 1/2, are both just constants. So what I'm going to do is I'm going to combine them into a new constant. I'm going to call that new constant K prime. And so I have K prime then is equal to Br2 to the 1/2 power times H2. And so my complete rate law, once again, would be rate is equal to K prime times Br2 to the 1/2 power times the concentration of H2. That will do it for the last installment of General Equilibrium, Unit 14. I'll see you on the next one. Thanks. Bye-bye.